Okay, today we will go over the properties of the Fourier transform. So let me remind you the definition of the Fourier transform. So given a signal x of t, the Fourier transform of x is defined through this Fourier integral. And of course, we have the inverse Fourier transform, which instead is given by 1 over 2 pi integral minus infinity to infinity of x of omega e to the plus j omega t in the omega. Okay? So the main properties of the Fourier transform are the following. Linearity. What does it mean, linearity? Here I'm going to do a column. Let's make a column of the signal and the correspondent Fourier transform. Okay? So linearity means that if I have a linear combination of signals, the correspondent Fourier transform is the linear combination of each Fourier transform of x1 and x2. Okay? Then we have the time shift. If I consider the shifted signal x of t minus t naught, the correspondent Fourier transform is going to be e to the minus j omega t naught x of omega, which x of omega is also the Fourier transform of x of t. Modulation. Or we can even call it a frequency shift. If I have the signal given by the multiplication of x of t with an oscillating amplitude at frequency omega naught, the correspondent Fourier transform is going to be that of x of t but shifted at omega naught. Then let's consider also the convolution. The convolution is telling me that if I have the convolution of two signals, the Fourier transform of the convolution of two signals is given by the product of the convolution. And that is one of the most important properties of the Fourier transform. Then we have the derivative. If the Fourier transform of dx dt is equal to j omega times x of omega. And of course, from this property, you can generalize it to the derivative of any order, which then becomes the n derivative as a Fourier transform j omega of n times x of omega. So the derivative of order n. Okay, so I'm going to show you, I will go over some of these properties. Let's try to prove it. But before doing that, let me show also another important property, which is the duality. So the duality, which we're going to prove it, and again, if we have a pair of transforms, x of t and its Fourier transform, I can get another Fourier transform for free, another Fourier transform pair for free, by simply taking the frequency, the Fourier signal in the Fourier signal, the Fourier transform, and make it as a function of the time. And then we will show that the correspondent Fourier transform is given by 2 pi small x of minus omega. Okay? And this is an important property because once you know one transformation pair, you're going to get another one for free. Okay? Given Fourier pair, get one for free. Okay? So, and these more or less are the most important properties that you need to master. And let's try to go over some of them and at least to see how to prove them. They are very straightforward, and it's a good exercise for you to become to get acquainted with the Fourier integral. Okay, so now the linearity is pretty straightforward. Because we need to show that if I have alpha 1 x1 of t plus alpha 2 x2 of t, the correspondent Fourier transform is given by the linear combination of the single Fourier transforms. And this is simply a result of the linearity of the integral operator. Indeed, the Fourier transform of alpha 1 x1t plus alpha 2 x2t is equal to the integral minus infinity to infinity of alpha 1 x1 of t plus alpha 2 x2 of t e to the minus j omega t d omega. But now I can use linearity of the integral, and I can write this is equal to alpha 1, the integral between minus infinity to infinity of x1 of t e to the minus j omega t t, plus alpha 2 integral minus infinity to infinity of x sub 2 e to the minus j omega t in d omega. But now I recognize that this is simply the Fourier transform of small x1, and this is the Fourier transform of x2 of omega. So this is pretty straightforward. Then we get these results. Okay? Time shift. The time shift is also easy to prove, because if we have a signal shifted by t naught, the correspondent Fourier transform is going to be e to the minus j omega t naught x of omega. Okay, how to prove that? Again, the same steps. The Fourier transform of x of t minus t naught is equal to the integral between minus infinity and infinity of the shifted signal e to the minus j omega t d omega. Now I can manipulate this expression, and I can add and subtract plus j omega t naught minus j omega t naught. By doing this way, I can bring these two things together and rewrite this as e to the minus j omega t minus t naught times this contribution, which I can bring it outside. I can split the two exponentials, and so this can be rewritten in this form, which means that this integral is equal to the integral with minus infinity and infinity of x of t minus t naught e to the minus j omega t minus t naught, and I made a mistake here is delta t. The integration is in time. And in delta t, and then I can bring outside j omega t naught. But now I can do the change of variable, tau equal t minus t naught, and delta tau equal delta t. This will allow me to rewrite the Fourier transform of the shifted signal as e to the minus j omega t naught times the integral minus infinity to infinity of x of tau e to the minus j omega tau in d tau. And this is simply the Fourier transform of x of omega, and then we prove the property. So pretty straightforward. So there are applications of properties of the integrals of a generic integral. Now